Okay. Good afternoon. Welcome back. So this will be a last session for um this program. So which I think we have actually talked about different additive manufacturing techniques, and we also talked about different materials and then functional materials by Professor Ravi, where he actually talked about different other in terms of how to prepare when it comes to traditional. And now, so we also gone through some of the additive technique, so in the previous class. So we'll try to cover some of the hybrid when it comes to the technology. So as I said, so this is like a brief, right? We will give overview. So we will see how much we can cover. But so just to give you idea that so when we talk about hybrid, right? So why we need actually hybrid first place, right? Why can't you actually go for a single or any one manufacturing technique, right? Why we need actually hybrid, right? Why we should actually go for again hybrid within additive, right? So so if you see that traditionally, right, if you actually talk about anything that you want to actually manufacture a product, or anything that you actually want to make a component, right? So if you categorize in terms of what are the different manufacturing techniques, that you will actually will find something like this, right? So you will find formative manufacturing process, which means you may have different dies or different molds, right? Example, if I actually talk about casting, or if I talk about molding, or if I talk about investment casting, right? All these things where you actually prepare the mirror of a actual part that you want to actually make, right? We are actually trying to get the component. Initially you are having a something like a mirror shape of what exactly the shape, or what component that you are actually looking for it. So as I said, including, right, we talk about forging, we talk about rolling, many things where you are actually trying to form a shape, or you are trying to make a, or you create the object which is basically where it can be usable. Now, so that is a one very broader, right? Under this you will actually find many basics, or basic manufacturing technique actually will fall under this category. Like if I talk about casting, or if you talk about farming, if I talk about anything that we actually try to get the shape by putting or pouring the material, right? Now here, when it comes to subtractive manufacturing, right, we actually talk about, think about, you already have the component or raw material. You may have different standard format or standard sizes that you may actually get through different shape or formative for manufacturing process. So including the casting, and then different traditional manufacturing where you actually form the shape, right? So and then you actually remove excess material, right, where you actually think that material may not be required, right, where you think you need to actually remove to form a shape. So example, this is your shape that you want to actually retain, or you want to achieve at the end of the where you want to actually make the component something like this, right? And then you need to actually remove that material wherever that you think it is not required, right? And then the third most, that where we actually talked about it, where you only add the material how much ever it is required, right? So that is where we actually discussed about additive, right? But if you see, there are so many advantages and limitation when it comes to individual processes, right? When it comes to individual technique, like if I talk about formative, right? So without you know molds, or without shapes, or without preparing the tools, in terms of preparing, like initially you may have a different samples, and then you need to actually go for a machining, and then you need to have patterns, and so many things that you need, right? So if I want to make a one single component, right, one part that I want to make, right, so you need to actually again start from beginning for making a the component, or making a pattern, and making a molds, and then etc. So I may consider that is actually kind of a limitation. If I want to actually achieve some part, and then I need to again, if I change the dimensions, again I need to actually go back, right? So that I feel maybe limitation. But what is the good thing about the technology, right? I can actually form the shapes, right? I can actually get the different shapes, and then quickly I can actually pour the material, and then I can actually get the component if I know exactly what I want to make, right? So, but if you see that, what is another disadvantage that you will find? The surface finishing of all this component will decided by where that you are actually processing, or where you are actually pouring the material, or what kind of a technique that you are actually using for making the material, or making the component, right? Like example, if I talk about rolling, or if I talk about casting, the surface finishing of your molds are very important, right? If a bad surface, and then you will end up bad surface on the part as well, right? But and then I see that when it comes to subtractive manufacturing, right? So if I talk about surface finishing, because when you actually go for high speed machining, right, so where you will actually find a really nice finishing, right? But and then there is a limitation. What is the limitation? Is about when you actually want to make any component, you need to actually remove a lot of materials. So which means you are going to waste a lot of the materials when it comes to subtractive manufacturing. But and then there is always easy. I mean, it is always easy. Say example, if I want to make a hole, right? If I want to make a pocket, right? If I want to make a hundreds of holes, or hundreds of this thing that you want to actually have pockets. In this case, it is a difficult, right? You need to actually change everything, right? Here it is easy. Now, so that is basically the advantage that we have. That limitation, we actually we need to have the dedicated machine tool for this. Like example, if I talk about the CNC machines, right? So there we need to have dedicated machines. Then only you will be able to get better surface finishing, etc. Now, when we talk about additive, right? It is yes good when it comes to quickly you want to get the prototype, right? You want to seek the prototype. You don't want to wait a lot of time, and you don't want to actually go for a multiple tools, and then wait for days, and for just getting a one simple component or simple part, right? So that's where it actually showed some progress. But and then as you start building it up, as you start using it up, and then you started actually comparing many things with the traditional manufacturing processes in terms of properties, in terms of surface finishing, right? So example, when you got the 3D printed part, and then you quickly realized it, I am getting better surface finishing when I go for subtractive manufacturing. And then when you simply again you suddenly started comparing, if I go for a farming, or if I actually go for a forging, right? If I go for a casting, I have different properties. Sometimes I get a better properties when I actually go for a forged components, because when you apply the forging on a component or already casted component, and then you actually get a better properties compared to additive, right? And then you started questioning. Yes, technology was good when I actually want to quickly build something, and I saw that lot of design flexibility, and then I saw a lot of material flexibility, and then I saw that. But and then once I got it, and then I started realizing it, that I should see how to reach the properties which is closer to traditional manufacturing process, which they had a disadvantage in terms of a design and in material composition. Now, can I actually combine it, where I can take advantage of each and every technique, right? So where I can actually use a hybrid, right? And then I can take advantage of, like example, I will actually make a component with additively, and then I can actually go for a better surface finishing by using a subtractive manufacturing process. Now, can I make hybrid component, where I can actually satisfy now where I was like having a advantage when I actually go for subtractive manufacturing. Now I'm actually taking advantage of each technology, making my component even better, right? Making my component more in terms of properties, or in terms of surface finishing, or so many things that was actually lacking or limitation when I actually go for individual process, right? Now can I actually make a component, can I actually go for a forging? Can I use something like a farming technique, where I can actually compress my additively manufactured component, right? Can I actually deform the material? Can I actually enhance my surface finishing by applying different deformation technique? Can I apply different subtractive manufacturing technique, so that I can actually enhance my surface finishing? Although I would like to may lose some material, but I want to have better surface finishing. I don't want to lose the material, but I want to have actually better properties. Example, we have a lot of techniques these days, like farming techniques, and then we have friction stir processing, etc., where it will actually enhance the properties of a 3D printed part. So that is where we need actually hybrid, right? So as I said, example, we talked about it, like where if we talk about the casting, or if you talk about the forging, so where it will actually help us quickly look into that geometric, but you need a lot of tools for making any object a simple object, right? So when it comes to subtractive manufacturing process, example, milling and then turning and then grinding, but and then there is a limitation when it comes to the technology, where you need to actually remove a lot of materials, right? But and then this is where we actually talked about some of additive, including welding, where you are actually adding the material, right, wherever it is required. Sometimes you need to actually add the material if you want to actually join few or two materials, right? So how now we can actually strengthen, or basically the individual take the advantage of the process, like where we saw that the strength of individual process, and then make the component better than before, right? So that is where, as I said, each process has a strength and then weakness that actually impact the design and then manufacturing feasibility. Now can we take advantage of each process and then make a product, right? So what is the meaning of hybrid? So you can have hybrid in terms of where you actually combine additive technique with the conventional manufacturing methods, right? Hybrid also can be within AM also, right? Sometimes you can also use within AM. Within AM techniques, like you may have different additive manufacturing technique. You can always also go for hybrid with other hybrid in other additive technique, but more or wider when it comes to the properties, or when it comes to the strength that you will have more when you actually go for combining with or multiple or conventional process than where you have that advantages when you actually combine additive, right? So this will actually help us to leverage the strength of the multiple processes to overcome standalone limitation, right? As I said, we found a lot of limitations when we actually go for individual manufacturing process. Now by combining this, we will be able to actually improve, right, many things, including mechanical properties, right? So there, where I will be actually covering some of the aspects of hybrid. So as I said, you will have a lot of flexibility in terms of materials and then mechanical properties. You can also enhance the printed parts and so on. Why we need hybrid, right? As I said, there are a lot of challenges alone AM, right? Example, whatever last few class that we have actually talked about, we did not actually deliberate on individual parameter, but when you actually start making a component, example, some of the parts you actually printed, you will actually notice these issues, right? You will observe these are the major issues when it comes to the additive, right? Example, surface finishing, you may find bad, or sometime you will find okay, this is just a prototype. But when you actually start printing actual component, you realize no, I need to have better surface. Prototype, up to prototype, you will feel okay, fine. So I just want to see the I want to feel the the part, and then that's all, right? But as you go more, and then you start looking different other parameters, and then you will find a lot of mechanical property constraints. So as I said, when you actually lay the material, right, so you are actually adding the layer by layer, which means so there is always issue when it comes to the bonding between the layers or overlaps, right? So and then when you actually compare with the traditional technique, like if you actually compare with the forged component, right, so you will not be able to achieve sometime, or you may need a more post processing to achieve the properties that are equivalent to the forged component, right? So and then lot of issues again, like restricted in terms of scalability for industrial applications, etc. So now what we are trying to see here is like combine, as I said, the strength of each or multiple technique, and then improve the productivity and then cost efficiency of the components that we are actually talking about it, right? So if you see this picture, right, so typically you will actually find this is what, say example, so if you want to actually make a better surface, right? So you thought like these are the basically, if you actually increase layer thickness, so you imagine that the bigger the layer, the larger the layer thickness, so you will actually end up a lot of gaps here. If I actually add another layer, it will go outside. But for that, I can actually reduce it by decreasing the layer thickness. But and then your process will be slowed down. But even then, you will still find your surface finishing may not be good. Now, if you actually see this picture, right, you add the excess material and only remove this material, some portion, and then you will see better surface finishing. So this is where we are actually achieving by combining two processes, which is here we actually add using additive, and then here you actually use subtractive manufacturing for removing excess materials. So if you see this, I think I will not go to the into deep, because we have already discussed different technique. Like example, we have talked about powder bed fusion, and then directed energy deposition, and then material extrusion, and then briefly we have actually talked about sheet lamination, and then binder, and then material jetting. So if you see their philosophy, right, all the techniques were actually adding the materials and the layer by layer, but you will actually find more issues when you actually start printing and then testing them, right? So there are different classifications that I will not go because we have already covered. So here we actually see that what are the configurations that when you actually go for individual, and then you will find a lot of challenges when it comes to the metal, because we actually see a lot of improvement in terms of printing of this metal parts, but at the same time we also see how they are actually comparable when you go for traditional machining. So this is how you will find most of the classifications that like example how we can actually connect additive with the subtractive, and then additive with the forming, and then you have the additive with the heat treatment. So when I talk about subtractive, including milling and then grinding, and then if I talk about forming, including deformation and including friction stir welding, and then we have heat treatment, you have the different way of doing a heat treatment for this thing, right? So these are some of the technologies that you will actually find. So I'll be actually covering mostly additive in terms of metal additive, but of course, so these are the same when it comes to the other polymer based or FDM techniques, right? So where you're trying to combine, like example wire arc additive with the milling, right? You combine with the directed energy deposition with the laser pinning and milling, and then you have the powder bed fusion plus polishing and then milling, and then you have the directed energy deposition, and then you have the friction stir processing, right? So what we do here is in subtractive manufacturing, or when you actually combine with the additive, how we can actually take advantage of this, right? We can take advantage of, as I said, mainly you will find enhanced surface finishing, right? So that was actually the limitation when we actually did alone with the additive, right? So where we actually were not able to achieve better surface finishing or quality of surface finishing, right? And as you keep on adding the layers, you may at some point also lose the precision, or surface will be pretty bad, right? And then, as I said, advantage that we saw, geometric complexity, where we were able to make any shape that you actually design, right? We will be in a position to print it, but and then we need to actually see how to improve the surface finishing of the printed component, right? So this is where we actually say example, as I think other day I gave the example where we actually combine, right, where use additive, and then you actually start removing the material. It could sometime the layer by layer, or sometime you actually print entire component and then remove the material later. So you can also see that how best surface finishing. Example, imagine your large scale component, right, and then you just leave it like this versus how this component is actually looking, right? So you can see that highly the subtractive manufacturing process here, but before that additively made component. So think about, if I actually want to use I want to make this using a casting or a formative process, how much time or how much tooling and you need versus making the component here. And then think about, like, if you don't actually use a machining, right, for this component, how the surface look like, right? So you can see that difference in terms of the parts. And then, as I said, a lot of them actually tried, and recently many researchers are also trying using a different robot method. They're using robots for milling also, where they can add the material here, and then other robot can be removing the material, sometimes layer by layer, or you can actually use after entire component is actually being deposited, right? So these are some of the examples where you will see that how you can actually use like example, if I want to actually make something components like this, and then versus where you actually add the material and then you actually remove the material and then add the few layers and then again you remove the material, right? You're actually building the component by having a combined in terms of the technologies, right? So where you will find say example, if at all you process it using any formative, so if at all you want to actually machine it, it's like difficult, right? You add the few layers and then you actually machine it and then you add the few more layer on the top, right? So you will find a lot of example. If you talk about another example like this, right? If you actually compare buy to fly, right, where you have the when you actually compare with the traditional machining, if you actually simply go for a machining versus adding and then removing material, they have a lot of case studies where they have actually found a lot of advantages and then cost cutting. That's where a lot of industries are actually switching now, that why they need to have additive in their companies. The reason, they're actually comparing this technique with the traditional manufacturing process and then machining, and then they're seeing a lot of advantages and then a lot of improvement in terms of additive and then combining. And many times, not necessary that every time that you need to actually use additive, right? But based on the part and then based on the time and then based on the material that you have, so you need to actually choose additive, right? So otherwise it will be difficult to fit everything if you want to actually make additive or if you want to use additive, right? So and then you have some more examples, like we actually use a different configuration for adding the material, and then you can see some of the component which is before and after, and then you will find a huge difference when you actually make the component which is made up of hybrid. Let me see if I can actually play this video. So you can see this is a component which is actually wire arc additive manufacturing, right? So this is how it is actually looking, right? But now you see that once they actually use a subtractive manufacturing for a surface finishing, and then how the part actually will look like. So you can see that, so after printing, so you started actually removing some amount of a material, then you will actually find a huge difference before and after. So that is how wire arc additive manufacturing. So we'll go to another case studies where you will find another examples. This is the powder based additive manufacturing, I think we have talked about this technology yesterday, which is directed energy deposition. So there you'll find how the part surface finishing actually will be different when you actually combine with the hybrid. So think about, see how the bad surface, like when you actually start making this component with a lot of sparks and then etc. Since we have seen this video, I'll just slightly
which is for less material, a lot of internal stress in a job. Fusion 360, which is slightly into perhaps then of the hot used. And seeing this technology.
So you can see this is the blade that you will actually see after the blade deposited through additive, and now you will actually go for subtractive manufacturing.
Also through our advanced material tooling, essentially only used.
So this is actually the milling. You can see that surface finishing is actually varying as you actually go for the machining. Yeah, you can see that how nicely the surface finishing now, before and after. Okay, so that's about the video. So again, there are so many other case studies that I can go on, since it's a limited time, so that I'll stop some of the examples. So this is another technique, I think, that we have actually talked about, ultrasonic additive manufacturing, where, so if you see that usually the sheets will come and then will form the shapes here when you actually use a different ultrasonic energy here. So where, and then you actually cut it, right? But you have a lot of excess material as well here, right, wherein we need to actually remove this the materials after that, right? So this is initially when you actually form the sheet. So you can see that how the sheet is actually being placed here. So this is where the sheet is actually coming. You can see that the sheet is actually, and then now is actually doing the milling, so that only that portion will be retained. Yeah, so this is another example that you will actually find how to take advantage of two different process. And you can see a lot of you can see the house how nicely the pocket is actually made, right? Imagine if I want to actually make this kind of component using a traditional or a single manufacturing process. It's a quite challenging, right? So yeah, so a lot of other ways that you can also see, like example, heat treatment, right? Once you actually make a or 3D print, so you can also actually go for a different heat treatment, where you can actually improve the microstructure and then improve or reduce the residual stresses or enhance the mechanical properties, and then you can actually have a different heat treatment. As you know that a lot of you actually working in materials, that you can actually change many in terms of properties, like when you actually go for a different heating after even printing, right? So I think this is another way where you can actually enhance your 3D printed part. And then I think a lot of work is also being done in the case of like where you can actually form the, not just removing the material, right? You can actually deform the material after depositing. Like example, you can use a different rolling technique, and then different other deformation technique. Here you can actually see that friction stir process also can be used for making. This is example, we have the setup here where I think Mr. Prashant is actually trying to deform the right after printing, where he is actually using the different the rollers, where you can actually see this rollers here, right? So right after printing, you will actually will try to make the shape, and then you can actually, you will be taking advantage of the heat which is already available, so that it needs less energy for deformation, or less energy in terms of making a better surface finishing, right? So I think our Sujata is again working on a friction stir processing, where she is actually enhancing a 3D printed part. Like example, you deposit a few one layer, and then you can actually process on that deposited layer, right? So like this, we have a lot of work is going on in terms of hybrid. And then this is another technique where you actually you see initially you will when you actually do that simple additive, you will find something like this microstructure. But when you actually go for a deformation or farming, right, where you can actually have better enhanced microstructure here, right? So this is just to give examples how you can actually change internal microstructure and then external surface as well when you actually go for hybrid additives. Yeah, so some more examples in terms of farming, which I will see. Example, you have that forging, where you have the different forge tools here, right? And then you can actually farm or remove the material. Here you can see that machined component versus forged components after printing, right? So I think I don't know whether I have the video of this. Yeah. Yeah, so a lot of example, we have the casting, right? I additive plus casted, right? So if you see that traditional casting, that where you need to actually go for a series of steps for making a any casting. Example, preparing the patterns, and then again you need to actually prepare the tools for that. So how about directly example, if you talk about the investment casting, right? So can we actually directly prepare the the part that actually your patterns, right? Example, if I talk about something like this, right? So if you see, this is what actually the typical investment casting process, where they have to go through. Example, where you prepare patterns, and then you actually use a different machining technique for preparing the molds, right? And then you actually dip into slurry. How about preparing this entirely molds, so that you can actually eliminate all these processes, right? You can actually directly pour the material inside, right? So this is the advantage of why we should actually go for additive and then casting technique. I don't know whether this video is coming now. I think we have already played this. Yeah, so this is actually the ceramic 3D printing. So and then we have also additive within like example hybrid additive, where you can actually go for some type. You may need to actually make a component which is a smaller, and then you want to also make a component which is bigger, right? And sometimes the specific or the technology, like example, if I talk about the powder, right? So that is actually good when it comes to making a small component. But if I actually go for making a larger component, right, now I have to switch technology, right? How about combining these technologies, right? Like example, if I take this big large component, but there are smaller components as well. Now I will actually segment based on the component size, and then accordingly I will actually use the technology. When it comes to the larger component, I will go for a wire DED, and then when I actually smaller component, I'll go for a powder DED, so that at the end of the day, in single station, I'll be able to actually get component which is both small and then large scale. So this is one part of the presentation. So I think I'll cover one more. Any questions before I actually take another 20 minutes to cover another topic? So yeah, that is actually a good question. So voids, see, you can actually go for wherever one is. See, anything that we actually talk about internal, anything that we actually talk about internal, voids or porosities. So we should go for something like where you actually apply some compressive load, which means you have to go for something like a deformation technique, right? So example, I think I showed you the example where when you actually go for rolling, or when you actually go for applying deformation, right? Which means you are actually trying to compress the material, right? When you actually when you try to compress the material, if any voids or if any porosities will be eliminated. But it may also happen that too much of when you apply too much force, it may also lead to cracks also. But you should know exactly how much you should apply load and which technique you should apply. But by uh, you know when technology point of view, we should see that how to reduce in first place, right? So that we don't need to actually go for post treatment. But if it is so you need to actually see that when only if you only want to go for surface finishing, go for machining technique. But you want to actually enhance properties of a printed in terms of reducing the size of the microstructure or reducing the any wires, etc., you have to go for something deformation technique, so that it will actually help in terms of reducing all the porosities. Any other questions? Okay, so I'll not take much time. Maybe I'll just brief about one more topic. So which is, I thought this may help for you as a researcher. Uh, I don't think, is it? Okay, so I think by now you got some idea that what are the you know additive manufacturing, and then what are the different ways in which you can actually make a component or 3D print, right? But as a researcher, there are still a lot of interesting or a lot of important issues that we can actually look into it, and then we can actually look at it, and then we can solve some of the things, right? So that is where I thought, like example, if you see that a lot of material, right? Of course, there is a lot of improvement if you actually compare 5 years back today. But still, when it comes to the traditional manufacturing processes, the kind of library, the kind of the data that we have may not have for additive. When I change it to the process, and then I need to actually generate again from beginning, right? So where you have a lot of limited materials option today, right? And then I think here, as a researcher, we can actually explore whatever the materials that are actually available, and then we need to see how to actually combine, and then see how they're actually, and how you can actually generate a lot of data, right, which is actually lacking, right? Even if you actually want to talk about anything that AI or ML, that if you're thinking these tools will actually will take in a smarter way, but first place you need to have the data, which we are actually lacking. This is, I think, one of the pressing challenge when it comes to additive, right? So, and then we see that lot of this technique, that example, you actually printed all the components. If you actually test it, and then you will actually find one properties. If you actually again print it evening or tomorrow morning, and then again you will actually find a different properties, right? It is too sensitive in terms of a technology. How to actually come out of this, how to actually make a standard set of rules or standard deviation for this kind of a process, right? So this is, the process is highly sensitive changes in terms of material properties. So the material have the limited shelf life also. Like example, if you actually talk about you actually buy some material, right? If you actually don't use it, and then you will face another problem, right? How to actually come out of that problem, right? And then lot of this material, right? Like example, each process support only family of materials, right? If I actually talk about proprietary 3D printers, right? And then example, FDM, right? So, or if I talk about SLA, right? So only this technology only is good for that, right? If I change it, the technology, right, and then I'll have a challenge, right? How to actually address, as a researcher, that we need to actually see how to come up. It's not about everything that we actually find a solution, but we can actually see the each and process and then material behavior, and then we can actually understand fundamentals of each technology, and then fundamentals of each how the how material actually behaves, right? So that is where, as a scholar, we need to actually develop that mindset, how to actually address this kind of challenges, so that we can actually generate or we can actually give more amount of the data, and then more in terms of flexibility in terms of usage, right? And then we actually have the where we see a lot of accuracy issues, and the strength, and then anisotropy when it comes to the jet especially, right? So you will find the poor properties, like, because when you don't actually manage well with your layers, right, you actually end up bad in terms of the poor in terms of properties, or if you actually compare with X and Y, right? So, and then we have a lot of other issues, like example, when it comes to the part, right, you will not be able to make 100% dense component, right? How to actually come about. So if you actually look into each and every process, you can actually define n number of problems, n number of a research problem for in terms of solving as a faculty, or as a PhD student, as a undergraduate, or postgraduate, where we can actually take many problems just at the one slide, that you will actually find some hundreds of different challenges. So and then addition to that, there are a lot of interesting things, like example, how to increase or how to make better in terms of I think we have talked about staircase effect. I think we have not talked much about staircase effect, but we have actually got, when it comes to that machining, we have actually tried to eliminate this effect. But still, why we need to actually go for a machining? Why can't we actually make as you actually build the top layer, why can't you actually go for something much better in terms of controlling of a material deposition, so that where you need a less amount of surface treatment, or less amount of material can be removed, right? So why can't we actually have something like a very innovative way of making or removing small material, instead of removing a large amount of material, which is we simply are using it when it comes to that subtractive manufacturing, right? So again, a lot of improvement that is actually happened when it comes to the prototype. Now people are actually using AM machines in different fields, but and then still the scale that was supposed to be still not, that is not actually happening. When you actually thought about like 10 years back, I was thinking that this technology will be used, especially metal will be used multiple places, but because of the limitation that we have in the previous slides that I have mentioned, still the technology is actually not taking the way that we thought, right? So of course, another example that we actually talked about, like where the surface support structure, that how to eliminate support structure, how to actually come up with a novel ideas or a novel technique, so that where least amount of support structure is enough for making or reducing, so that you least depend on the support structure, or even if you actually put the support structure, how to minimize support structure, right? Or how to minimize post processing, right? So these are the some of the is under when it comes to the slicing, that you will actually find many things interesting, that when you actually go for a uniform slicing, right? So it will simply will create the each layer with a standard the thickness. How about going for adaptive slicing, right? Based on the shape, based on the size, based on the complexity of my component, can I actually change the slicing technique? Can I actually orient my slicing technique? I mean the slices. Like example, if I see the component, so up to here is fine, I can have uniform slices. How about as soon as I come here, instead of making a uniform slices, can I actually reduce the slices? Only this portion. But when I go for at the top, and then can I actually, why only I should actually deposit in this direction? Why don't I actually deposit like this? And then why don't I deposit like this? And then can I actually pick, or can I actually cut it? Like example, I cut this area, and then I'll only prepare slices for this area, which is called adaptive slicing. Now, can I actually segment part into multiple sub components, where I choose based on how best I can actually make a component without going for a post treat or post processing, or where less in terms of a support structure, etc. How I can actually adapt, how I can use this kind of slicing, so that I can actually eliminate different in terms of surface finishing, right? So this is example that how I can actually use a uniform versus adaptive the slices, right, where I can take advantage of this thing. And also you will actually find when you actually change from uniform to adaptive slicing, you will see number of slices also will actually will reduce it, right? Why do you need to actually go for same layers? Like I know that there is no variation in the thickness, or there is no variation in the part. Why I should actually deposit hundreds of layers there? Why can't I actually reduce number of layers, increase the layer thickness, and then make it a small number of layers, right? So that I can actually, as you know that if you actually reduce the number of slices, which means you are actually increasing, in terms of increasing the speed of printing. Because earlier you may be having uniform slicing 750 slices. When you actually go for adaptive slicing without staircase elimination, you will have 251. Adaptive slicing with staircase elimination, you will have 11 slices only. Simple one technique that it actually changed the way that I actually manufacture a component. Just a simple technique that by just varying the slices, I will be able to. But again, you need to have that amount of material to you are able to deposit that material in each slide, right? You need to have that capability on your printer that this much material can be deposited as you change your slices thickness. But even then, many cases that when you actually go for uniform versus, you can actually reduce more than 50% of slices, which means you can actually increase your speed of machines by at least 50%. Initially, it is maybe taking 3 hours, but if you can actually effectively slice it, it will take 1 hour 50 minutes or 1 hour 30 minutes. All that you need to actually do, use the right slicing strategies. Nothing you need to do, just see that how path plan and then how the deposition can be varied, so that you can actually take the advantage of just the slicing. And then you will also find a lot of changes or advantages when you actually go for adaptive slicing. If I go for uniform slicing, this is how it actually look like, and then you may actually end up losing a lot of materials here. But when I go for adaptive, you can see that as soon as I come here, I'll have more layers where there is a curvature here, right? Here there is a curvature, but I followed the uniform slicing. When I do that, so I actually have some of the material is actually not depositing because your slice thickness are uniform. Based on this curvature, I can actually decide what is the layer thickness, right? If I actually draw the line, and then I can actually see that the gap or the distance between each that layer, if I actually keep constant, so it will come something like this, right? So there is actually dedicated formula that you can actually decide how the layer thickness supposed to be when you actually draw the horizontal line. Sorry, vertical line and horizontal this thing, you can actually see that. So this is simple example that will change the way actually we look into the problem, right? And then these are some of the examples that you will actually find. These are all just changing the slicing, right? Example here, you see that adaptive the uniform slicing, where you will actually find a lot of test steps. But here, when you actually go for adaptive slicing, but component is same, just that I've actually changed the slice thickness based on the curvature or based on the component side, or based on the feature that I actually want to 3D. I will actually cover or print even smaller parts, right? So I think, and you have some more components that find when you actually versus example. This is right, and then you have the adaptive slicing. You see that how component this versus this, all that you're actually changing. You're changing only you are looking into more of a design aspects, more of a path planning that you are actually looking at it, and then you are actually fixing before even to start manufacturing. So these are all actually comes under design for additive manufacturing. So whatever I am talking about it, so since we did not actually cover, dedicated class for design for additive is one of the topic that will play a major role when it comes to the additive manufacturing, without which you will not be able to get proper in terms of component, both in terms of surface finishing and then the part that the properties that you actually achieve. So I can actually go on like this. There are so many examples. Like example, here you see that when you actually go for the adding the material uniformly, and then you will not be able to build. This is without support structure. Here also I'm building without support structure, but and then I'm actually having it controlled in terms of the material, so that I'll be able to print without even support structure. But all that I have actually varied the this thing. Uh, and of course, lot of other slicing technique, example visibility based slicing, that where especially when it comes to the die and then mold, where you can actually find the slices, or where you will not be able to see them, but you will need the slicing such so that you can actually deposit that much material inside the molds, where it is not easy, or in terms of simply you cannot actually use simple methods to manufacture or 3D print such kind of a components. So example, if I talk about some of the examples, like we have cases like where, example, this one, not sure if this video is.
These are some impressions of what could be possible with the next generation of 3D printing slicers. Completely overhanging surfaces.
So you can see that this is overhanging surfaces without putting the support structure. You can see how you will actually manufacture.
Of slicing, and how even you can contribute that they become a reality soon. Let's find out more. Guten Tag, everybody. I'm Stefan, and welcome to CNC Kitchen. This video is sponsored by Squarespace. Easily create the website you've always wanted, or replace your old one that you always hated. Save 10% by visiting squarespace.com/CNC Kitchen. Current 3D printing slicers are done. What I mean with this is that even though they are slicers for 3D printing, they simply stack two-dimensional layers on top of each other to form your final part. There are basically no movements within the G-code instructions where all three axes move simultaneously. That's why current 3D printing slicers are rather 2.5D slicers. But why are they using this approach? Well, simply because it's mathematically easy, and honestly because this approach works remarkably well. Yet, we are leaving a ton of potential on the table because 3D printers are easily capable of complex three-dimensional moves. Yet, we don't have any software to take advantage of it. Over the last few years, 3D printing slicers didn't really change a lot besides being way easier to use and much quicker. Yet the general slicing approach always stayed the same. Cut a three-dimensional part into a two-dimensional slice, draw the perimeters around the circumference, and fill the rest with one of many infill patterns. The only real evolution we've seen this year is the Arachne perimeter generator, first seen in Cura, that dynamically adjusts the width of the extrusion for more details and less gaps. Still, everything is on a two-dimensional plane, which causes the typical stair-stepping patterns on sloped surfaces and, of course, requires supports on overhanging structures. Over the years, we have seen a couple of approaches of non-planar slicing, often to improve top surfaces, yet none of them ever really made it into a mainstream slicer. Though quite recently, we've seen a couple of really impressive ways of 3D printing parts that have previously been deemed impossible by using really clever slicing approaches. One of them is non-planar conical slicing. A bunch of weeks ago, I've shown this technique in my Rodbot video, where I visited the University of Applied Science in Winterthur, Switzerland, where they built a 4-axis Prusa printer that can manufacture complex overhangs without the need for support structure. Yet the best thing is that we can use the same slicing approach on a regular 3-axis printer to achieve very similar results. And this isn't just an idea published in a paper, but you can download the Python script necessary and try this out on your own parts and prints.
I also uploaded a bunch of sample G-codes and printables for the not so programming savvy. If you print them or even slice your own parts, please share the results and spread the awareness around this method, and maybe consider subscribing to the channel for more like this in the future. So let's quickly talk about the idea behind this approach. Common FDM 3D printers are able to print quite steep overhang angles, yet at some pop out the need for support. That will be a volcanic shape by simply moving the points of the mesh upward is better. Generated into fuzziest look like, because the bigger just good enough to tool that we article role if you want to print
So that's, I think, the pretty much that I think I have covered. So any questions? Okay, so thank you all. We will again come back at 4 o'clock. Okay, so we will have last session of this workshop. Thank you all once again.